Hello everyone, I am G. Shweta, working as the assistant professor in the Department of Electrical and Electronics Engineering. So in St. Martin's Engineering College. So today I'm going to give a video lecture in ideal and practical transformer. So first we'll discuss about the what is transformer. So transformer is a static device which is transforms the electrical power one circuit to another circuit without changing the frequency. So let us we are going to explain about ideal transformer. So in the ideal transformer, no iron and copper losses, no leakage flux and no winding resistance. So this ideal transformer is 100% efficiency. These are the conditions for the ideal transformer. So next we'll discuss about the what is the working principle of the ideal transformer. In the ideal transformer, primary side we are connecting the primary side we are connecting the supply voltage, secondary side we are connecting the no load condition. So in the primary side we are giving to the supply voltage, so the current I0 current is passing through the primary side winding. So in the primary side flux will be produced. So due to that presence of flux, the induced EMF will be generated in the primary side. So the same flux will be linked with the secondary side. So in the secondary side also EMF E2 is generated in the secondary side according to the Faraday's law of induction. So and here secondary side I2 current is 0. So next we'll discuss about the phasor diagram of the ideal transformer. So in the ideal transformer, no load current is produced in the ideal transformer. So that no load current is divided by two currents, that is the magnetizing current, one more is the working component current. So this magnetizing current, which is the magnetization of the core, this working component current is the which is responsible for the losses of the transformer. So this is the phasor representation of the transformer. So in the ideal transformer, I0 current is very small. So I am taken as flux as the reference. This is the flux of the taken as the reference flux. So this magnetizing current. So in the ideal transformer, no load current is equal to magnetizing current. So these magnetizing current is lags by the 90 degrees with supplied voltage. So V1 which is lags current is lags by the V1 with 90 degrees. So in the here, due to this flux, EMF will be induced in the primary side and secondary side. So these E1 and E2 induced EMF, both induced EMF are antiphase with the supply voltage. So these E2 is E1 and E2 are both are the in phase. These E1 and E2 are antiphase with the supply voltage. So E2 is equal to V2 and E1 is equal to V1. This is the phasor representation of the ideal transformer. So next we'll discuss about the what are the advantages of the ideal transformer. There are no losses like hysteresis and eddy current losses and copper losses. Voltage and current ratios are perfectly based on the coil. There is the no leakage flux of the ideal transformer, and this is the perfect linearity of the ideal transformer. In the ideal transformer, 100% efficiency. So next we'll discuss about the practical transformer. So in the practical transformer, we are having the losses and winding resistance and leakage flux. So these in the practical transformer, efficiency is very less. So these are the conditions for the practical transformer. So next we'll discuss about the practical transformer at no load condition and practical transformer at load condition. So in the practical transformer at no load condition, so we are connecting the practical transformer is primary side is connected in the voltage, secondary side no load condition. So in the practical transformer, we are having the leakage flux and we are having the losses and we are having the leakage flux, we are having the losses and we are having the winding resistance. So this is in the practical transformer, efficiency is very less. So in the ideal practical transformer, so no load current is divided by the two currents. So one is magnetizing current, so one is working component current. So in the coming to the ideal transformer, working component is negligible because of that their ideal transformer no load current. So coming to the practical transformer, both currents should be present in the no load condition. So because of these magnetizing current and working component currents both are present in the practical transformer, because of in the practical transformer we are having eddy current and hysteresis losses. So next, coming to the phasor representation. So here I am taking as the flux as the reference. These are the flux of the practical transformer. So both no load current is equal to magnetizing current plus working component current. So the resultant of the practical transformer I naught is equal to I magnetizing plus I working component. So next, coming to the phasor representation, I am taken as flux as the reference. So both current and flux will be in phase with the in phase. So here magnetizing current is lags by the supply voltage with 90 degrees. So working component current and supply voltage is both are in phase. So the resultant current, both I magnetizing and I am magnetization current and working component current, both are resultant current I naught is equal plus I working component current. So this is the phasor I naught, the resultant of I naught current is equal to magnetizing current plus working component current. So here both EMF E1 induced EMF E1 and E2 are the both are the in phase. This E1 is equal to V1, E2 is equal to V2. So these both E1 induced EMF primary side and secondary side EMF both are the antiphase with the supply voltage. So next we'll discuss about the practical transformer at on-load condition. So this is the practical transformer diagram of the on-load condition. So this is the schematic diagram of the practical transformer at on-load condition. So here primary side we are connecting the supply voltage, secondary side we are connecting the load. So these practical transformer is acting as the resistive and reactive and capacitive load. So purely this practical transformer is purely reactive nature. In the reactive nature we are having the capacitive load, inductive load and resistive load. So in working principle of the practical, let us discuss about the working principle of the practical transformer. So here primary side we are connecting the V1 voltage, secondary side we are connecting the load. So in the primary side I naught current is passing through the primary side winding. So then flux will be produced in the primary side winding. So when the flux will be produced, according to the Faraday's law of electromagnetic induction, EMF E1 is generated in the primary side winding. So same flux will be links with the secondary side winding. So here also E2 is generated in the secondary side by these flux will be passing links with the secondary side due to magnetizing core. So next here secondary side I2 current is, secondary side we are connecting the load. So secondary side also I2 current is passing. So whenever I2 current is passing through the secondary side winding, so the flux will be produced in the secondary side also. So the same flux will be links with the primary side winding. So that flux will be phi 2 flux. So next here I2 current is small amount of the current will be links with the primary side current. So this is for primary side, so I naught current, secondary side I2 current. So this I2 dash current is secondary side current is links with the primary side current, that is I can assume as the I2 dash current. This I2 dash current is also known as counter current. So here in the practical transformer I1 resultant current I1 is equal to no load current plus counter current. So this is the resultant current of the practical transformer. So next let us discuss about the resistive load, inductive load and capacitive load of the practical transformer. So in the resistive load, so voltage and current should be both are the in phase of the in the practical transformer, current and voltage should be in phase. Next in the practical transformer secondary side, here let us discuss about the resistive load of the practical transformer, resistive load with on load condition. So resistive nature. So in the I am taken as flux, all the flux is the reference. Next flux, these flux will be reference. So here magnetizing the total resultant current I1 is equal to I naught no load current plus counter current I2 dash. This is the resultant current of the practical transformer. Next, here high magnetizing current. So flux, this current will be, this current is lags by the supply voltage V1 with a 90 degrees. So working component current and supply current both are the in phase. The resultant current of the magnetizing current plus working component current is no load current. So this is the practical transformer at no load condition. So coming to the practical transformer at load condition with resistive load, So here EMF E1 and E2 are this. So here E2 is equal to V2, E1 is equal to V1. So here both EMF E1 and E2, primary side E1 and E2 are the, both are the in phase. These both EMF E1 and E2 are the anti-phase with the supply voltage. So next we'll discuss in the resistive load. So I2 is the in phase with supply voltage. This is the I2. So next this I2 is I2 dash is counter current. So this I2 is mirror reflection of the I2 dash. So this is the practical transformer at no load condition. So the resultant current I1 is equal to I0 plus I2 dash counter current. So this is the mirror reflection of the I2 dash. So these I2 dash and I1 is the co-intersect at one point. So that should be resultant current of the practical transformer at load condition. So this is the flux pi 1, this is the flux pi naught at no load condition. This is the voltage and resultant current flux should be pi 1 flux. This is the resistive load of the practical transformer. Next we'll discuss about the inductive nature of the practical transformer. In the inductive nature of the practical transformer, so the current is lagging, so the current is logging. In the next we'll discuss about the inductive nature of the transformer. Well, next we'll discuss about the inductive nature of the transformer. So next, inductive nature of the practical transformer. So these are the advantages of the transformer. So next, what are efficient and electricity transformer, voltage level adjustment and safety, and cost is efficiency of the practical transformer. So next, phasor diagram of the transformer at on-load condition. So in the practical transformer, so in the inductive load, so flux will be reference. So in the inductive load, current is the lagging with supply voltage. So this is the current. So this current should be lagging with the current. This current should be lagging is supply voltage. So the resultant current in the inductive nature, the resultant current is I2 dash. So I0 is equal to I0 plus I2 dash. So here in the practical transformer at inductive load, flux is reference load. So magnetizing current and working component is equal to I no load condition. So next, in the practical transformer, I1 is equal to I2 dash plus I no load current. So in the current is here, current is leading, I2 current is leading. So I2 current is here, mirror reflection of the I2 dash. This I2 dash current is the counter current. So both I0 current and I2 current both are the intersect at the one point. That point should be resultant current. So I1 is equal to I0 plus I2 dash. So these I0 and voltage will, angle between I0 and voltage is the flux pi, and next I1 and V1 is the angle between the I1 and resultant current I1 and supply voltage V1 is the phi 2 flux. So next we'll discuss about the capacitive load. So next, in the coming to the capacitive load in the practical transformer at load condition, this is acting as the capacitive load. In the capacitive load, current is leads with supply voltage. So here also I am taking as the flux as the reference. So the no load current is equal to magnetizing current plus component current, and resultant current I1 is equal to I2 dash plus no load current. So here I2 dash is the counter current of the practical transformer. So in the practical transformer, current is lagging, current is leading with supply voltage, right? So here leads the I2 dash current is leading with supply voltage. So I2 dash is I2 is mirror reflection of the I2 dash. So here the resultant current I1 is equal to I0 plus I2 dash. So I0 plus I2 dash. These I2 dash and I1 are both are the intersect with the one point. That point should be resultant current of the practical transformer at capacitive nature. So this flux I0 and I1, both angle between the I0 and I1 is the flux pi naught, and angle between I2 and E1 is the both flux pi 2. So here induced EMF E1 and E2 are both are in phase. These induced EMF E1 and E2 are the antiphase with the supply voltage. So next, coming to the advantages of the practical transformer. So in the practical transformer, efficiency, electricity transmission, voltage level adjustment, this is the safety and cost efficiency wide. So in the practical transformer, so efficiency less. So in the real time we are using the practical transformer. In the real time we are not using the ideal transformer, because in the ideal transformer only no load current is present, nothing but I0 is equal to magnetizing current. So coming to the practical transformer, so in this practical transformer we are using wide range applications. So in the real time we are not using the ideal transformer, real time we are using the practical transformer at load condition. Next, coming to the auto transformer. So next we'll discuss about the auto transformer. So auto transformer is a special type of the transformer with only one winding. That winding is laminated with core. That winding is, the single winding is wounded with the silicon steel laminated core. So this is the construction of the auto transformer. So this is the schematic diagram of the auto transformer. In this schematic diagram, so which is laminated with the single winding. So some part of the single winding is acting as the primary winding. Next, some part of the winding is acting as the secondary winding. That the number of turns of the auto transformer can be varied by using the switch contact. So the output of the auto transformer is, the output of the auto transformer can be varied. So it is called as the variac and voltage regulator. These auto transformer we are using the, we can regulate the voltage, output voltage, so which is also called as variac or voltage regulator. So next, in the normal transformer, primary and secondary, both windings are magnetically coupled, but electrically not isolated. Coming to the auto transformer, both windings, primary and secondary windings are, both windings are magnetically coupled and electrically connected, this auto transformer. So coming to the in the auto transformer, what features of the auto transformer. So primary and coming to the features of the auto transformer, primary and secondary both are the electrically isolated, and useless copper should be, useless copper is, primary and secondary winding, both windings are electrically isolated, useless copper, and hence it should be very cheaper. The transformation ratio differs from unity, so higher efficiency but smaller in size, lower leakage and lower losses, so increase the kVA rating. So in the auto transformer we are using the voltage by we are using, so increase the kVA rating. So these are the features of the auto transformer. So next, coming to the applications in the auto transformers are used to compensate the voltage drops in the transmission and distribution lines. So auto transformers are used to reduce the voltage supplied to an AC motors during the starting period. So auto transformers are used in a continuously variable supply. So these are the applications of the auto transformer. So next, coming to the auto transformer, I will explain the auto transformer working principle. So next, in these auto transformer is special type of the auto transformer with only one. So this auto transformer is winding with only single winding. So this single winding is laminated with core. So the winding is, this single winding is wounded with silicon steel laminated core. So these one, some part of the primary winding is acting as the primary, some part of the acting as the secondary. So in the secondary side of the auto winding, so we are connecting load. So this works on the according to the mutual induction. So next we'll discuss about the video about transformers. So this is the we are going to explain about transformers video. So next we'll discuss about the video how it works transformer in the real life. So here primary side we are connecting supply voltage. So this is supply voltage of the primary side. Secondary side we are connecting load. So this is the secondary side of the transformer. This secondary side we are connecting load. So next here the primary side current is passing through the primary side current is passing. So this current should be primary side and secondary side, both should be current is passing. So here primary side, so whenever current is passing primary side, so the current, the sinusoidal waveform of the transformer from positive to negative complete one cycle. So next here the whenever current is passing through the primary side, so the current is passing through the windings. This is the how it flux will be links with primary to, from primary to secondary. So coming to the load, so this is the primary and secondary of the transformer. So next coming to the so based on voltages, we are having two types of the transformer, step up and step down transformer. So we'll discuss about step down transformer. So primary side 20 turns, we'll giving to the secondary side 10 turns. So here we are supply voltage is 120. So here what is the formula of the step up transformer? V secondary by primary equal to secondary by primary. So supply voltage V is equal to 120 voltage is 10 turns by 20 turns and nothing but secondary side N1 by primary side N2. So the resultant supply voltage is equal to 0.5 into 120 primary side voltage. So this is the supply voltage finally is 60 volts. So this is the working principle of how it works, the working principle of the transformer. So how it works, how it is how it based on voltages, how it works. We are having two types of the transformer, step up and step down transformer. So what is the sinusoidal waveform of the transformer from primary to, from passing from positive to negative, and secondary side also from 0 volts from positive to maximum to negative. So these are the how it works, how current is passing through the primary side. So next secondary side flux will be produced in the primary side due to this current. So this same flux will be links with the secondary side. So how it the here based on step up transformer primary side, this is the step down transformer. So primary side number of turns is high, secondary side number of turns is low. So this is called as step down transformer. So let us consider this is the 20 turns primary side, 10 turns and secondary side let us consider. So 120 voltage of the primary side, this is the formula for the step down transformer. Secondary side and primary side transformer is equal to total secondary by primary side transformer. So next will taken as the 10 secondary side turns and 20 turns. So we'll get finally supply voltage V is equal to 0.5 into 120 by into primary side voltage. So supply voltage finally will get V supply voltage is equal to 60 volts. So this is the complete complete working principle of the primary and secondary side of the transformer. So next, this is the brief explanation of the primary and secondary side of the transformer. So how it works and how it generate the flux and how current is passing from primary to secondary. So how flux will be produced from primary to secondary. So next, how we have to find the supply voltage and how we have to find the step down transformer of this supply voltage, and this is the complete discussion about the ideal and practical transformer of the no load and on load condition. And this complete ideal and practical transformer, in the real time we are using only a practical transformer, we are not using the ideal transformer. So ideal transformer we are using only theoretically, but practical transformer we are using practically. So next, this complete brief explanation of the ideal transformer, and next ideal and practical transformer, what are the differences between ideal and practical transformer, next we'll discuss. So next, ideal and practical transformer. So in the ideal transformer, no leakage flux, no winding resistance, and no winding resistance, no leakage flux, no hysteresis and eddy current losses. Coming to the practical transformer, we are having the losses, we are having the winding resistance, we are having the losses, we are having the winding resistance. And so in coming to the ideal transformer, 100% efficiency. Coming to the practical transformer, less efficiency. This is the differences between ideal and practical transformer. So next, we'll discuss how flux will be produced in the video and how EMF will be generated in from primary to secondary. Complete a brief explanation in the video. Thank you.